what are hypergeometric functions? 1 over 1 minus x is the simplest example of a hypergeometric function. They're so far away from trigonometric functions and hyperbolic functions that, they seem totally unusable, right? So what are they good for? Why do we use them? Well, that's what we'll be talking about today. So first of all, question 1. What is a hypergeometric function? Well, as you can guess from the name, it has something to do with geometric series. Now, recall that a geometric series is the infinite sum of x to the n, where we're summing over n, the index. And, that's pretty much it. So, it starts off as 1 plus x squared plus x cubed plus x to the fourth, and so on and so forth. And there's a pretty easy proof that this is just equal to 1 over 1 minus x. So how does that relate to hypergeometric functions in general? Well, as you might have guessed, the hyper is because hypergeometric functions are generalizations of geometric functions. Instead of being just x to the n, we now have some function f of x and multiply it by some function g that might depend both on x and on the sum index n to the nth power, which means it has to increase or decrease, but its power or influence is going to increase as you go on. And an important distinction is that this has to be a rational function. Otherwise, pretty much anything could be hypergeometric. So, okay, we know what they're for now, but why are they useful? Well, as you saw before, 1 over 1 minus x is the simplest example of a hypergeometric function. And that guy pops up everywhere, with slightly more advanced one. Well, how about x to the n over n factorial? That one's pretty easy, right? This is just e to the x. And that's another hypergeometric function. Where's the evidence? Well, at the end of the day, f of x is 1, while g of x and n to the nth power is 1. Well, as n increases, what's happening? Let's take term k plus 1 and compare it with term k. Clearly, the only thing that's happened is a multiplication by x over k plus 1. Increases the factorial on the bottom and the power on the top. Which means that the function g of x comma n is actually one of the simplest rational functions. It's just x over n plus 1. And that just gets repeated over and over again. There it is. It's a hypergeometric function, folks. So, now that we know what a hypergeometric function is, what is it actually useful for? Some of the easiest hypergeometric functions are useful for other things, but what about the more enigmatic ones? Well, let me introduce you to a problem that a certain Jacobi was attempting to solve all the way back in, I think, the 1770s or 80s. So everybody knows, you want me to move to the blackboard? Everybody knows that a circle has some ratio to its radius. Sorry, a circle's circumference has some ratio to its radius. How do you formalize that? Well, you take an arc length integral. So how do you take an arc length integral? Well, you take the curve. You know what? Let's switch to blackboard. Probably going to be easier to explain. You take this curve, you split it up into differential line segments. And then, for each of these, this gap is dx, and this gap is dy, hence the slope being dy dx. Well, this is unofficial. Technically, dy dx is not a ratio, but it helps with intuition. So what's the total length of this curve? Well, just use the Pythagorean theorem. It's a finite sum of, what's this? This is the square root of dy squared plus dx squared. So it's a finite sum of dy squared plus dx squared over all of the line segments. If you're feeling really funky, you can rewrite this as dy squared over dx squared plus 1 multiplied by dx. We factored out the dx. So this is for the finite sum, but of course, since the number of line segments approaches infinity, finite sum, just like a Riemann sum, is going to get turned into an integral. So it's going to be the integral of the square root of 1 plus, this is just the derivative squared, dx, over, well, whatever range you want to integrate over. So, how does that work for a circle? You take the defining equation of a circle, or at least of the upper half, which is implicitly x squared plus y squared equals 1. Then you can split it into two halves. The positive root and the negative root, which just gives you the lower half of the semicircle. Sorry, the lower semicircle. And so, all you have to do is take the derivative of that. And what's the derivative of this? Well, it's just going to be d dx of 1 minus x squared to the 1/2. Which is, by the product rule and chain rule, you take the 1/2 out, you install a minus 1/2 here, and you multiply the rest by the derivative of whatever's inside, minus 2x. So you cancel these two out, and you get minus x over the square root of, well, this doesn't matter since we're squaring it, 1 minus x squared. And so what happens when you put that in here? You get the integral from, well, what range are we integrating over? -1, which is where the semicircle begins, to 1, which is where it ends, of, well, what's this squared? It's the square root of 1 plus x squared over 1 minus x squared. And actually, you can combine this to get the square root of 1 over 1 minus x squared. Or 1 over the square root of 1 minus x squared dx. If you're not familiar with this, this is the reason that arctan's derivative is 1 over the square root of 1 minus x squared. And this is another definition of pi over 2. Because realize what we just did, the reason the bounds are from -1 to 1 is because that's the end point and beginning point of the unit semicircle. So we just measured the perimeter of the unit semicircle with this integral, which is of course half of the full unit circle. Okay, so there it is. Solution for a circle, simple. Well, actually not that simple, because there's not a great way to represent pi. The only good ways are with infinite sums or infinite products, but those don't count as closed forms. So, that sucks. What about the problem for ellipses? Now things get a little bit more general. Not only do you now have to ask about both a semi-minor and semi-major axis, but back when we were dealing with circles, if this sector and this sector had the same exact angle, then that meant the arcs they subtended had the same circumference. I'm now realizing that it's probably better to rub them. So that is not true with the ellipse, obviously. If this, oh well, it is, no, it's not even true with 90 degrees. So you can pretty obviously show that this length, exactly 1/4 of the ellipse's total length, the ellipse's total circumference, is not equal in the slightest to, if we take a random line here and draw the perpendicular, it's already very easy to see that this length is a lot smaller than this length, despite both of the angles of the arcs being 90 degrees. Which means we now also have to specify position. The ellipse is not rotationally symmetrical. So things are bad all around, if you couldn't tell. How do we deal with this? This is thankfully where hypergeometric functions come in to save us. So, oh wait, no, let's move to the whiteboard. How do hypergeometric functions save us in this situation? Well, first of all, let's consider what the equation of an ellipse is. It's x squared over a squared plus y squared over b squared, where this is semi-minor, this is semi-major, is equal to r squared. Well, no, it's actually equal to 1. This is what it's dependent on. So, how do we work with this equation? Well, it's quite simple. We try to find a similar form for the semi-ellipse. So we multiply both ends by b squared, and we get y squared plus b squared over a squared x squared is equal to 1. So we move it to the other side and make this y squared is equal to 1 minus b squared over a squared x squared. And so y is equal to the square root of 1 minus b squared over a squared x squared. That was fine. But now comes the really difficult part. What do we do with this? How do we integrate this function when b squared over a squared isn't equal to 1? Sorry. Well, this actually looks totally different now. Because the arc length integral is 1 plus y prime of x squared dx. And so what's y prime of x here? It changes because of the chain rule. And so this is going to give you minus x minus b squared over a squared x. Let me put that, oh no, that canceled out the 1/2. Divided by the square root of 1 minus b squared over a squared x squared. And so you can unite this all under one banner and get, you move the a squared back down to the bottom where it belongs and get minus b squared x over the square root of a to the 4th minus a squared b squared x squared. And so what happens when you plug this back in here? You get square root of 1 plus, this doesn't matter, b to the 4th x squared over a to the 4th minus a squared b squared x squared. And as you can sense, things are already going off the rails. So how do we even approach this? Well, first of all, we test the tried and true method of bringing the 1 over, which gives us a to the 4th minus a squared b squared x squared plus b to the 4th x squared. Normally these two would cancel, but a is not equal to b. So that means that we are stuck, right? Well, here's the good part. What we can do is take this square root of 1 minus b squared over a squared x squared term and expand it using the generalized binomial formula. And what we get is n equals 0 to infinity. When you have that minus there, this is going to be minus 1 to the n multiplied by, this is going to be the factorial for 1/2. And unlike the technical definition of the factorial as rad pi, you go with the discrete definition. So 1/2 factorial is actually more like 1/2 multiplied by negative 1/2 multiplied by negative 3/2. And of course that one doesn't converge. This is just an analytical extension using the gamma function. So what do we do about this? I think this would be over 2, by the way. So what do we do about this? Well, now, because of 1/2 factorial expanding, or you can put it more like a finite product from k equals 1 to n of 1/2 minus k. So, oh, and this is just going to be b squared over a squared x to the n. So, because of the way this works, because of the fact that, well, what's the ratio between two of these consecutive terms? It's going to be minus 1 to the I plus first term is I plus 1 product from k equals 1 to I plus 1 of 1/2 minus k multiplied by b squared over a squared x to the 2i plus 2. And you divide that by minus 1 to the I, so this cancels out and just gives you minus 1 times the product from k equals 1 to I of the exact same thing, which means all of this product is going to cancel out and only leave you with the I plus first term, minus 1/2, multiplied by b squared over a squared, so that cancels out in the end, and x to the 2i, which means this cancels out and gives you x squared. Now that is a fairly rational function if I've ever seen it, and hence it can get classified as a hyperbolic function. Sorry, a hypergeometric function. Now these little numbers tell us exactly how many inputs the hypergeometric function is taking in. In general, the hypergeometric function looks something like this. You have alpha to some power, beta to some power, gamma to some power, and these are all independent functions of x and n. And you have alpha prime to some power, beta prime to some power, ... And the number of elements here on the top is, let's call it A. Number of elements on the bottom is B. This is AFB. So now in this case, it's 2F1 with the specific values minus 1/2, 1. And that is the hypergeometric function. Of course, this reduces all the way down to pi for our good friend whenever a is not equal to b. But otherwise, whenever a is equal to b. But otherwise, it takes on this pretty nasty form. So, one last thing you might be wondering is, this makes no sense because it has nothing to do with the eccentricity, the semi-major or semi-minor axis. Well, that's because this has just been assuming an ellipse with some eccentricity such that either the semi-minor or semi-major axis is equal to 1. And then the semi-minor or semi-major axis is adjusted accordingly due to the eccentricity being set. In reality, this is, of course, proportional to A, like all circumferences, and this is dependent on the eccentricity. No, that's not the symbol he used. So, once that's done, you finally have a hypergeometric representation for an ellipse's circumference, which means that hypergeometric functions are useful for pretty much everything. They allow us to give a nice, clean, closed form to things that are so monstrous and incomprehensible that they can't be assigned any other label.